So the interesting thing about galaxies is that we didn't even know we had such a thing as galaxies until, the last 100 years, really. So anyways, galaxies are really give us an idea of how big the universe is and how many stars are really in our universe. So we know a good bit about stars, hopefully at this point. We know that they come from gas clouds, collapsing the gas clouds, and we know that stars tend to form planetary systems. Okay, but now we want to look at larger grouping of stars called galaxies. And they're different than just star clusters. Star clusters you find within galaxies. There's smaller grouping of stars, but really large grouping of stars that are bound together via gravity are called galaxies. They're little islands of stars, so to speak. And they were thought of as islands in the sky long time ago. They used to call them nebula. So if you find old astronomy books, prior 1920, 1930, you're going to see this reference to islands or nebula in the sky. And those were actually what we now know of as galaxies. So we've come a long way since then. And if you haven't looked at any of Hubble's deep field images or Hubble's ultra deep field images, I would encourage you to do so. You could go to the Hubble site and look that up, or the NASA website has archived images from Hubble as well. Or you could just Google those terms, the Hubble deep field, and you'll get these extraordinary images of peering back in time, which we call look back time, because we're looking at light that left these galaxies. And some of these are like over 13 billion years ago, they left the light of these galaxies. So this image right here that I'm showing is 13.2 billion light years away, goes back in time 13.2 billion light years. That's distant, and that's light from a very long time ago, close to the age of our actual universe, which we'll talk about in tomorrow's lecture. So here we are peering back in time, and we get all these images of all these different galaxies. And galaxy classification is complex. There's some citizen science projects out there in which they want people to help them classify all these galaxies and go through the data. We're constantly finding new galaxies, and we're constantly understanding new ways that they're evolving. Okay, so here we have, in this image, we have about 10,000 galaxies packed in together. Okay, and these are based, putting these images together, you're using combination of ultraviolet, visible, and infrared light to look at all these images. So really fascinating images of galaxies. There's so many. Whoa. Okay, so when we talk about galaxy, as I mentioned, it's just a grouping of stars, gas, dust, interstellar medium, and dark matter, and that are all gravitationally bound. So star clusters are smaller groupings of stars. So when we talk about galaxy, we have this bound object, kind of like our solar system is a bound object of our star, the sun, and all the debris that orbit it, that are connected via the force of gravity. Well, the same thing with the galaxy. We have a bunch of stuff all connected via gravity. And what we have is we have a lot of stars, and we have a lot of star-making regions inside our galaxy. But even more puzzling is that we have a lot of matter, like 90% of our galaxy, our own galaxy, which is the Milky Way galaxy, is comprised of this matter that has no detectable, it gives off detectable wavelengths that we could see, but there is mass there, and that's called dark matter. So we're trying to find hints of what this dark matter is, how it behaves. Still a mystery. We have dark matter detectors, trying to understand more about it. So we have this invisible matter out there that makes up most of our galaxies. And in a later slide, we'll see how we know there must be some other matter out there. And this is how we came down the road to understanding dark matter a little bit more. And its involvement in galaxy formation is through the orbital speeds. Okay, so these are all gravitationally bound. So how many galaxies? Well, 100 billion and counting, right? So this is how much we've counted in the observable universe. And there's a lot of really sophisticated programs trying to still map out our universe. And you can imagine how much of an undertaking that is. We've only covered like, 35% of the sky with a project called SDSS, which is the Sloan Digital Sky Survey. They map out the entire universe. So they're mapping it out galaxy by galaxy and all the other objects at a time. And that's a big undertaking. Gaia is one of the missions responsible for measuring parallax to these stars. And that helps us to map out the distances and the spread of all these objects, galaxies in particular, in our observable universe. Okay, so one of the thoughts that you want to think about, especially now and if you're out observing at night, is that all the stars that we see in the night sky without any aid, no binoculars, no telescopes, are the stars in our galaxy, our own galaxy, the Milky Way galaxy. Okay, so we could see with telescopes, we could see stars in other galaxies, but we're limited to our views here of our own galaxy. Now we can see the furthest distant, the most distant object a person can see with the unaided eye is the Andromeda galaxy, which is one of our neighboring galaxies, the next biggest galaxy to us. And that is like 2.5 million light years away. So this is an object that's also cataloged as a Messier object, M31. And you could see it in the night sky. It's if you look for the Andromeda constellation, if you take out your star wheel right here, and you look for it in the Andromeda constellation, you will find the Andromeda galaxy. So I'll point that out when we get there. So it's something that you could see in the summer night sky. And that's always a good thing to try to, get people to look for when they're beginning astronomy and trying to understand how to navigate through the night sky. It's a little fuzzy patch. So this was noticed earlier in the night sky observations. Okay, whoops. So lots of galaxies, 100 billion and counting. So now we could get into extreme detail on galaxy classifications, and I'll mention some of the notes on this. I might add some notes onto our page on this because there are some details on the different galaxy classifications. But the main galaxy classifications we have to date are elliptical galaxies. Okay, and there's a picture of an elliptical. The very first one on the left is an elliptical galaxy. It's a spherical flattened sphere shape, and it has little gas and dust and mostly composed of older stars. So these guys have been around for a long time. Okay, so ellipticals were one of some of the very first galaxies that formed after the beginning of our universe. Next, we have spiral, and you'll see that we have different kinds of spirals. So here's a typical spiral galaxy. So we have a disc shape. So this is an image of a spiral galaxy here in the center. We have a disc shape with a bright center and spiral arms that rotate. And they containing lots of stars, gas and dust, and dark matter. Now, younger stars and star formation happen in these spiral arms. So these are moving around these spiral arms and rotating. And as you collide if portions of gas and dust collide in these segments, then that triggers star formation. So these are huge star forming regions. And eventually this gas and dust will run out and there'll be no more star formation in the process. Okay, so here we have a typical spiral galaxy, and then we have some that are just irregular. There's like no shape or pattern to them, and we just have lots of gas and dust and interstellar material that contain young blue stars. And again, many of these patches of galaxies, these regular galaxies, were early galaxies in the formation of our universe. So these are some of the first galaxies were elliptical and irregular. Now, some spirals are believed to be old as well, but most spirals are formed via the collisions of ellipticals, irregulars, and irregulars. So note that there's a lot of subclasses of these, especially with spirals. We have the term barred spiral. Our Milky Way galaxy is considered a barred spiral galaxy. Now, some big ideas here. The main factors that influence a shape that we know of so far are the mass, how much kilograms you have packed in there, how the matter is distributed at the beginning, right? So where are the pockets of gas and dust? And then if you have one area where you have more pockets of gas and dust, that'll form, that might form the actual center of the galaxy. So the distribution of matter is key. And the big role in how that's distributed is how the dark matter makes the luminous matter stick in the actual galaxy. The rotation, so how fast it's spinning and flattening, plays a key role in what the galaxy will look like and the type it becomes. Perturbations, so shock waves, collisions, these play a big role in how the galaxy actually forms and how it comes to the shape it has currently. So collisions, we'll see, are key in forming a lot of these larger spirals that we see. Oops. Okay, so now we have something called dwarf galaxies. These are a type of galaxy that we're really finding out more and more of recently. And we're starting to count these. There's so many of them. They're the most abundant type of galaxy out there. So there's a lot of tiny little galaxies, small galaxies called these dwarfs, and there are millions of stars, up to several billion. Now, for comparison, our own Milky Way, which is a barred spiral, is considered a fairly large galaxy, is 200 to 400 billion stars. Okay, so dwarfs are much smaller. There's so many that are being discovered. This is definitely like a gold rush for astronomy, the gold rush of galaxy findings. And the big thing is, are these a result of larger galaxy interactions and collisions? Are there leftover patches from bigger collisions? We don't know. Now, some examples are the Sagittarius dwarf elliptical galaxy that's 70,000 light years away from the sun in our closest galaxy to the Milky Way. Supposedly, some of these figures change and textbooks have to change to stay updated with this. So for a very long time, we thought the Andromeda galaxy was the closest galaxy to us until we could start seeing through the gas and dust, especially using Spitzer and infrared astronomy. We were able to see through our center and see that we actually have a smaller dwarf galaxy close to our center right there. Okay, so here we are. We're out on one of the spiral arms of our Milky Way, and here we have a dwarf galaxy close by. Okay, 70,000 light years away is much less than Andromeda, which is 2.5 million light years away. Okay, here's a typical look at what a dwarf galaxy looks like. Okay, just a small little patch of stars, gravitationally bound. Okay, and galaxy formation, and this is something that is really being explored and updated, and changing a lot. I mean, there's been a lot of changes just in the last 5 years. So very complex, but here's a big outline. And we'll talk about the Big Bang, which is the birth of the universe tomorrow. So we have like all that matter and energy in a small little dot called a singularity. It explodes, and we have all this hydrogen and helium that's spread out. And so we have these gases. H stands for hydrogen, He is helium. And then we have all this matter that's cooled down, and it's forming different clumps in different parts of our universe. So these irregularities in how the matter developed become these, what we call these proto-galactic clouds. Okay, proto-galactic, you know, just like we have protostars, we have proto-galactic areas. And then these clouds gravitationally collapse together. So we have this collapse, and we have this fragmenting and contracting of the material. Now, what happens is we have a lot of the matter, the kilograms, that we can't see. So this non-luminous matter, which is luminous matter, is the matter that we see every day, that we see interact with stuff, all the matter that we can see, all the kilograms we can see. But this dark matter that has no visible radiation provides this framework. So it makes, so we know that if you have mass, then you create a gravitational field. You attract other pieces of matter, right? That's the kind of the rule of law in astronomy, right? Matter, and then you have gravity act on you. So mass, I should say mass, and then you have gravity act on that mass. So we have all that mass from the dark matter that is clumping together all the luminous matter that we know of. So it provides like the scaffolding of the actual galaxy. So then all the luminous matter sticks to it, and then it starts forming this, we have this dark matter web, and we start forming these large scale structures and shapes, which are like the elliptical galaxies we see, the elliptical galaxies, the irregular galaxies that we see, and then every once in a while the spirals. But again, those tend to form via the collisions of other galaxies. We get these densities of star-forming regions, and stars are formed in the clouds, mainly hydrogen and helium again. Okay, so our current thoughts right now are small groups of galaxies gave way to later galactic structures, mostly irregular and elliptical, but some large galaxies too. And over time, larger and larger groups formed via the collisions and galactic cannibalism, where you have galaxies that merge together. And so when they collide with one another, we call that galactic cannibalism. So they merge and they become as one. And so, or, you know, sometimes if they're uneven amounts, if we have a bigger galaxy colliding with a smaller galaxy, it gobbles up that smaller galaxy. And that's what we mean by galactic cannibalism. And then the more we get these mergers, what happens is this contains a really active period. So as galaxies collide, what happens is all that gas and dust get shockwaved, right? So they're colliding as well. So this triggers a lot of star formation. So the star formation goes on for a period of time, but eventually you run out of that, and there's no more galaxies to collide with. And then the eventual demise of our universe is that all star formation will end as we use all those pockets of gas and dust up in our galaxies. So here's a quick little video on galaxy formation. I'm going to show this because this is a good visual. And I also have this on our website. So this is kind of what I was talking about. I'm going to shut my door for a second. So you could see simulating these are takes a lot of understanding of how much mass is involved in the galaxies. So how much mass is there, and then how fast the speeds are going, and how the matter is distributed. All those factors really play a role in doing these simulations. And there's a lot of researchers working on these simulations to try to get a better picture of how the galaxies form. And so we're trying to understand more about those. So there's that's definitely one that was done by the Royal Astronomical Society, which is a really good resource. Okay, so that gives you an idea of how that you got to picture this dark matter in there for, you know, sticking, getting those the luminous matter to stick in its formation. So it's really hard to imagine that there's all this like invisible matter that you can't see that's playing a role, but it's there, and we know it's there via the orbital velocities. Interesting stuff. Okay, so this is based on Edwin Hubble. And we'll see that he plays a key role in, you know, early galaxy identification and some big theories in cosmology, a big milestone for cosmology back in the 1920s, the redshift of galaxies. But he had an early classification scheme, which is still somewhat used today. There's an article on, Physics World has an article on how this is, you know, out of tune. We really need a new way of classifying galaxies, but this is what we've used for a long time, and we're finding that, you know, there are a lot of exceptions to these rules, and, you know, a lot of things we can't explain. But the idea is we have the ellipticals are on the left, and then we have two groups of spiral forming on the right from these. So what we could actually have collisions that form some of these spirals, and we have two types of spirals there. So we have the elliptical, and then we have our spiral shapes that are derived from those. So this is his tuning fork classification scheme that's been used for a long time. Hey, it might be something that might be totally omitted soon as well as we learn more. But according to this tuning fork scheme, we still use and label a lot of galaxies that way. So E is what we stands for elliptical. S is the label we give for spiral, and we have three subclasses, A, B, and C. SB is what we classify as a barred spiral, and we have three types, A, B, and C. And I stands for irregular. We have two types, irregular 1, irregular 2. So you can see how this classification scheme begins to get complex, or just trying to classify galaxies in general. So you could think of any galaxy you want, like the Pinwheel Galaxy is a very interesting galaxy to look up. You look that up and you're going to get a classification label that comes along with it. So some examples, we have the elliptical, we have M32. Okay. We have another one, NGC 4621. Okay, spirals, M31, which is the Andromeda Galaxy. As I mentioned, that's our nearest large spiral, nearest large galaxy that we could see with the unaided eye, and the furthest object we could see with the unaided eye. We discovered it to be a barred spiral a little later. And then we have the Milky Way is SBC. So it's a barred spiral, C category, and then M83 is a SBA. So here we have, if we look at these, we have SA, SB, SC. So here we're going to a decreasing bulge in the center. Okay, so the bulge in the center is where you have the densely packed population of stars. We call it the nuclear bulge too, the nucleus of the galaxy. So here we have a lower population, we have a more rotation, makes it flatten out and spread out. So You can see the difference between the SA, SB, SC, and for the barred spirals, you could see the difference in the bars here. So barred spirals with decreasing bulge and increasing arm openness. So here we are with the Milky Way. We're all the way over here. This is what our own galaxy is beginning to look like more and more so. Okay. And then irregulars are just here off to the side. And they're into two different classes, but again, they have no distinct shape or pattern to them. So we're still trying to learn more about these patches of galaxies. So here we have the mass relation for galaxy classification. So what happens is, as your mass increases, okay, this is what your shape is going to look like. And as your angular momentum increases, okay, so angular momentum again is the relationship between your mass and your spin rates. As more mass is packed towards your center, the faster your spin. Okay, so you're going to get different features based on those. So here we have the early spirals and a late type spiral, ones that have been spiraling for a while. These lenticulars are a class in between ellipticals and spirals. Okay, so this is another, these are in between, haven't quite formed, haven't quite been distinguished as one class or the other. So we have these in the process of becoming spirals. Now, some other interesting features of galaxies, we know that we have to look at them in a lot of different wavelengths of light to understand a lot of the features. So here we have a we have it viewed in radio wavelengths, infrared, which allows us to peer through the dust, visible light, which is what we've been limited for so long and obscures the view of a lot of features, ultraviolet, and then we have X-ray view here. So it's interesting to look at when you're looking at a galaxy and trying to interpret its information, that you're looking at all wavelengths of light, because that really gives an indication of what's going on. And then I have a link here to the galaxymap.org, which is a really good site, and I'm going to bring that up here. Okay, that really gets into a lot of interesting features and different wavelengths of light of different galaxies. So, and there's a lot of stuff on mapping out our own galaxy there. So this is something that I have a link to in my slideshow, but I could also post a separate link on our page so you can look at this Explorer. So it has a lot of different wavelengths you could explore with the Milky Way Explorer. And the Milky Way being our own galaxy, and you could take a look at it in so many different wavelengths. Okay, to look at it in infrared, different types of infrared. Here's what the X-ray looks like, etc. So that's a really useful link and site in exploring more on our different galaxy features. Okay, so now that we got kind of introduction on the basic types of galaxies out there, and I'll make a few more notes too on these types and how they form differently. Let's first look at our own galaxy, the Milky Way. And again, once believed to be a nebula, so it's been a puzzle for a long time. It was puzzling just to understand our own solar system and that fact that we went around the sun. So you can imagine how mind-boggling it was to understand that we have the sun solar system as part of a bigger grouping of stars, which is called a galaxy, and that we're going around the center of our galaxy. Now, a long time ago, well, I shouldn't say not too long ago, it was believed that we were this flattened disk, but now we're starting to see these curved tails on our Milky Way. So it's actually warped and twisted. So the recent images of our Milky Way and the recent mappings have found this twist along with our the edges of our galaxy. So here's our galaxy, and we're a barred spiral type of galaxy, and we have about 200 to 400 billion stars. So on average, we say 300 billion stars. So that part's not quite exact yet. We're still cataloging the stars, and some stars are dimmer than others and hard to actually count. So the age of our galaxy is approximated to 12.13 billion years. And we know this via the globular clusters, the older stars that are centered around, that are around the center of our galaxy, around the bulge in our center. Okay, so we could get comparison about their stellar evolution with other stars, and we could actually trace their age to about that to 12 to 13 billion years. So it's a big science of trying to narrow down what the age of those stars are. But again, being older stars, and then understanding some of these variable stars in the center, which we'll talk about, we get more of a hint of where they are in their stellar evolution based on their size and luminosity. And then we could put an age to those processes in their star evolution years. So anyways, this is a big science. So anyway, that's our current estimate. Now, to put this in perspective, the age of our universe is about 13.8 billion years old. So you could see that we have stars that are like, you know, a billion years from the Big Bang. So it's not too long after the Big Bang that all these older stars have formed. Okay, now the size is not, I have to update this real quick. I just noticed a typo. I was going to put 1,000, 100,000, because we talked about this figure before. There we go. All right, a little edit, quick edit. We have about 100, the scale here, as you could see, this is the radius from the center out, goes up to about 60,000 light years max, okay? So we have a diameter all the way across is about 100,000 light years, 120,000 light years across. That's a huge distance. So to get from one point to the other will take a very long time. So you could imagine the incredible task and trying to map that span of space right there with all the stars in there. That's a lot of space to cover. In the center is, we could see it here, but how do we see it from Earth? Well, we can only see it at certain times a year, our summer months, because there's sometimes, based on our positioning in the Milky Way, sometimes where we could see the center is viewable, but other times of the year where it's not viewable. Now, the center is located in the constellation Sagittarius, Ophiuchus, and Scorpius, a mixture of those constellations. And we have a central object called Sagittarius A, right ascension, 17 hours, 45 minutes. So this is what you most likely got around that figure when you plotted the clusters in your last quiz assignment. You know, you might have got something anywhere between like 16 to 19 hours as far as the location is sufficient as far as your quiz goes, because we were, you know, doing a lot of estimates there. But this is the exact location of our central object, the very, very central point of our Milky Way galaxy. And in that location, right here in the center, is a supermassive black hole. Okay, and how do we know? Well, we have lots of densely packed stars that are whipping around there at fast speeds, not just stars, but also gas and interstellar material. I mean, gas and dust. The material are whipping around there really fast. So there's a lot of collisions there too that are being produced, and lots of light emission because it's very active. That central part is very active, and there's high emission, lots of radiation that is being emitted from that area. We see the emission in X-ray, gamma rays, and radio. The optical light gives us no clue of what's there. So there's been many of a conquest in trying to get good images of the center of our galaxy and trying to understand the center. Now, a supermassive black hole is much larger than a stellar mass black hole. So you don't want to get those two mixed up. Supermassive black holes are found typically in the center of large galaxies, such as our own. They used to think that pretty much every galaxy would have a supermassive black hole, but now that's being revised again. So we're just finding them really in large galaxies, and they're millions to billions the mass of stellar mass black holes. So remember, stellar mass black holes are singularities. So these we have a lot of mass packed into a small space, a small radius. So when some stars die that have a lot of mass, that mass shrinks down to a very small scale, and then it has a small radius in which small radius called the event horizon. Once you go past the event horizon, you're in that black hole region. And that's a singularity where the light cannot escape because the gravity is so strong, it will not even let light escape, the fastest speed that is known to us. So stellar mass black holes are typically less than 100 solar masses. 100, they're 5 times the mass of the sun, 10 times the mass of the sun, 20 times the mass of the sun, just depends on that star. So 100 solar masses and less, but when you're comparing that to millions and billions the mass of stellar mass black holes, these are huge. These are large black holes, but all the same properties hold, meaning that they have event horizons that will be bigger because they're higher mass. So you could calculate the event horizon for any black hole using what's called the Schwarzschild radius, and it's a little algebraic formula you could use. And so you put in that mass, and you could figure out at what point what the radius is where you will not see any of the light from the black hole. You will see the light surrounding the black hole, but you will not see the light inside the black hole beyond the event horizon border. So these are going to be typically larger event horizons, and you have a lot more activity around them because black holes have a lot of gravity, right? They're very massive, so there's a lot of gravity there. So it's going to tend to make a lot of the objects around it orbit quicker and quicker, very fast speeds around there, and a lot of high energy emissions from the collisions of the objects surrounding that black hole. So we can't actually see the black hole because, again, there's no light there, but we see the objects surrounding black holes that give us evidence for them and allow us to understand them. Okay, so here we have an image. These are recent images taken by the Meerkat Observatory in South Africa. And this is done in radio light. So here we have 1,000 by 500 light year span of the Milky Way. And we're seeing all this activity in radio wavelengths. We also see an X-ray and gamma ray wavelengths as well. But these filaments around here, this is a really interesting picture, were discovered in the 1980s and they're still not understood. So here is the center of our galaxy, and there is where we have a supermassive black hole, which you can't see. So we're hoping to get more and more information on that. Okay. So one more note too, to make a supermassive black hole, you could figure out how to make the Earth into a supermassive black hole, what the event horizon is. But like, again, it would be something that had a lot more masses combined with a larger event horizon. So coming back to the center, looking more about, exploring more about the center of our galaxy. This is what it looks like here. We can see this in optical light. We could see Sagittarius is the teapot right here. Okay, so this is a constellation Sagittarius, which is a teapot. I've been seeing this every evening in the southeastern sky horizon. So in that direction, if you were to look, you'd be looking close to the center of the Milky Way. Okay, now we'll see the band of the center of the Milky Way, which is just like, it looks like the stream of milk, hence called the Milky Way. That term is adopted from the early Greeks that talked about a stream of milk being spilled in the sky. But it looks milky due to the high population of stars that are inhabiting that area, right? So more light, it's going to be, you know, more whitish in the sky. It's like if you're driving towards a city population, a densely populated city, from afar, you'll see that there's a lot of light there that you're heading towards. Okay, so the actual center part we see is part of Sagittarius, and there's Scorpius. They don't have Ophiuchus in here, but it's in this little square right here. Okay, and it's a fun thing to locate in the night sky. So see if you could see Sagittarius, which is also the teapot. Sky and Telescope has this updated image of when to view Sagittarius and where you could see it, what times you could see it. So I'd encourage you to go to their site. You could also use Stellarium and pull that up. You could see it on your star chart or the interactive sky charts that are out there. Okay, so this little square is our center area. Okay, and how do we know this is a center? Well, that took a lot of work, really fascinating work. So as you have done with your quiz, we use globular clusters and measuring their distance using something called Cepheid variable stars. So the oldest stars in our galaxy are in the center, in the halo center of our Milky Way. I mean, these are the globular clusters, found in these globular clusters. Now, the big trick was finding the distance to these globular clusters. How do we do that? Well, we use something called Cepheid variable stars, which were based on Leavitt's work. And then Shapley was the one who wanted to plot the globular clusters and try to figure out the distances to these Cepheid variable stars. So what are these Cepheid variable stars? Well, in the HR diagram, there's actually another strip called the instability strip. So we talked about how you go from the main sequence and then you start, you know, you leave the main sequence to become, like our sun in particular will leave the main sequence and become a red giant. Okay, in that process, a lot of stars are unstable. They're pulsating, right? As they're running out of fuel, they're expanding and they're pulsating. They're expanding and their luminosity is changing. So what we mean by pulsating stars is the luminosity, the brightness is changing over time. So the different stars pulsate at different rates depending upon how big they are, the size and mass. So what we have is Cepheid variable stars they're found in the instability strip of the HR diagram, and your book has a really good little image on that. And they leave the main sequence stage as they run out of fuel. So the pulsation period, your book says, I think it's up to 60 periods, but it could be anywhere from a few to 100 days. Okay, what we're finding is that there's really two types of Cepheid variables now. So just think of something that's pulsing, you know, every few days or up to 100 days. So the period of the variation, the pulsating variation, is related to the luminosity. The more massive, the more luminous. And if you're more massive and more luminous, it takes longer to pulsate, okay? You have a longer period of pulsation. And that's via the period luminosity relation. So what they did early on is they mapped out how luminous a star was and what the period of pulsation were. And by taking that relationship, they could actually get some estimates of how far away these stars are. Okay, so this should look familiar. This is kind of like what your quiz is, but I'll show you what my key looks like, but these are the very first maps of the globular clusters that Shapley put together using the work of the Cepheid variables. And you can see them clustered about a certain in a certain portion of the sky, which is of course the center of our Milky Way. So we began studying these clusters in 1914, and not much at all. You have to remember that not much at all was known about the shape of our Milky Way, let alone that we had these things called galaxies. So these variable stars were used as standard candles. And what we mean by that is that we know their absolute magnitudes, and we can use them by knowing their absolute magnitudes and the mass, the luminosity period relationship. We could figure out the distance using that and parallax together. So parallax was a big key as well. We could measure the distances to nearby stars using parallax. So any Cepheids that was close by, we could use parallax to, and then we could compare them out to further out Cepheids by knowing their absolute magnitudes and figure out deduce their distance that way. So really interesting science going on here, but it was a really put together the first best estimates on distances and where these were, where the center was. So globular clusters were found to be centered around this one spot. Okay, so if you averaged all this out, like you were asked to do on your quiz, right? You would find it would average out towards a certain center. It would average out to the center of the galaxy. Which is at 17 hours and 45 minutes. Okay. So here's the main components of our Milky Way here. We have a disk, which is most of the gas and dust. Okay, this comes from rotating and flattening, a lot like our solar system formation. The bulge, what we have is it's a center, dusty older stars right here. Okay. And then we have the halo, which is, again, this is where we have a lot of our surrounding spiral. It contains the stars and the globular clusters. So we have the central bulge, the nucleus, the very, very center, and then we have this halo here. Okay, and you can see the globular clusters just mapped out around the center here. Okay, those are the main regions. And again, what we're finding is we have also the spiral arms of our own galaxies. So you could add in arms, and your book has a lot of good information on there. You can see the spiral arms here, and that's where most of our star forming regions are. Okay, this is like a lot of older stars in that area. Oh, and there we are. Where are we? Now, a lot of these arms are still being investigated. So, you know, this is something that's always changing. We know we at least have 2 arm spirals, and there's, we think that there might be 4 or 5 at this point. Okay, so you could see how this is spread out. And here we are. Here's where the sun is. We usually call this the Orion arm. Here it's called the Orion spur. Okay, so we're right in this position, and we are about 28,000 light years from the center. Okay. And what happens is, for us, our solar system to go around, so we're in the suburbs of our Milky Way, it takes about 230 million years to go around that center. And that's mind-boggling, because when you think about it, the last time we were in the same position around the center of our Milky Way galaxies, there was dinosaurs on the Earth. So that's really a mind-blowing thought when you think about it. And of course, you know, we're going around the center of our own Milky Way galaxy. But then we have our galaxy that's also moving away, receding with all these other galaxies. So the current question is, how many arms are in the Milky Way? We still have to really pinpoint that and narrow that down. Okay. Now, big thing to understand as far as how our Milky Way, to understand more about our Milky Way, what we're trying to do is understand the mass in the Milky Way, because that really dictates how fast everything's spinning and all the stuff that we have here. So what is the mass of the Milky Way? Well, it's huge, and we're still processing the numbers. What we can do right now is we could find the mass based on the orbital motions of the sun and the other stars. Now, the best way to estimate the mass, if we go back this way, is to estimate, here we are with the sun. What we do is we estimate, we could figure out how fast we're going around, okay? And we could estimate the mass within our orbit. That's a lot easier based on our rotational speeds, which we have good information for. It's a lot harder to estimate the mass outside of our orbit. So for all the other objects, stars outside that are further out from the center are harder to predict. Okay. And what we do is we use Kepler's third law and a mix of Newton's laws. I like to derive this in physics class. It's a really, to find this orbital velocity law. You're not responsible for knowing this. I might show an example of how this works, but know what the orbital velocity law is and how it's related to these variables, but you won't have to compute anything. The way this works is mass within one star determines the outside orbit speeds. So further out mass is, as I said, more complex to do. And one of the main first indicators that things were amiss with our galaxy, and that we weren't able to account for all the mass that there is the fact that we were seeing the speeds that were much faster than we predicted. So there must be more mass in the Milky Way than we could actually see, because we were spinning around at a faster rate, had higher rotation speeds. This orbital velocity law is this mr is the mass within the orbit. So we could say, let's say we wanted to find the mass within the sun's orbit, right? This would be unknown. We would take how far we are out from the center, which was 20,000 plus light years. We would get the orbital speed of our actual galaxy. You could look that number up and square it. And then we would divide by the gravitational constant, the universal gravitational constant, and we could find out the mass that from our orbit to the center. Okay, so this is how you find the mass of our Milky Way, but other galaxies as well. So here's some thoughts. The Milky Way is part of a group of nearby galaxies called our local group, about 30 of these. So this number has been very changeable because we've been finding more of these dwarf galaxies that have been shrouded and covered with gas and dust we couldn't see before. Okay, so the two main members of our local group are the Milky Way and Andromeda. They account for the majority of the mass of our local group. Okay, so here we have a lot of dwarfs, irregulars, and galaxies. So this is our little local area. And this is part of this supercluster of galaxies called the Virgo supercluster. So here we have a view of our Milky Way, and right there is where you can see the Andromeda galaxy. Okay, look for that little hazy patch of sky in the summer. If you were out in a dark sky site like in the desert in Arizona and New Mexico, you could really, really see the Milky Way galaxy stream in the summer skies. So again, this is something visible in the summer because opposite time of year we can't see it. It's not viewable from our positioning on that arm with respect to the center. So right now is a good time to look at the central region of the Milky Way, look at our Milky Way galaxy and try to find the exact center. Now we are predicted to collide with this Andromeda galaxy. So here we are, the Milky Way in the Andromeda. We're on a collision course with Andromeda. So this is not going to happen for about 4.5 billion years. And this is when the sun is predicted to become a red giant as well. So when we do collide, what's going to happen is we'll become like this super huge galaxy, and we'll have a lot of star forming in the process. But once that dies down, we might have no more stars form for a while. Okay. So galaxy distances are tricky. So just to kind of put things into perspective, which will help us with some of the cosmology topics tomorrow, as we've shown earlier, we have Cepheid variables. They played a role in locating the center of the Milky Way. But we could also use Cepheids. We found them in other galaxies, and that gives us a way of measuring these distances to other galaxies. Okay. Edwin Hubble used these in the 1920s to estimate these galactic distances. So if you're really close, if you're trying to find the distance to, let's say, the moon or a close object in the solar system, you just use radar. Okay. Radar is when you take a light wave, like you shine a laser to the surface and it bounces back. That's what we mean by radar. And that's how we know the precise distance to the moon, etc. Nearby stars, we talked about parallax, very helpful. Okay, and that gives us a good basis for the further out stars. So then we do the Milky Way, we do the main sequence fitting. Understanding the evolution of stars really helps us put distances to perspective. And then the nearby and Cepheid variables and nearby galaxies. So Cepheids are right here too as well. Nearby galaxies, Cepheid variables. And then what we start looking at is we look at galaxy clusters, and then finding out distances between galaxy clusters. So this is what we mean by the cosmic distance ladder. All these different methods that astronomers use to determine these distances. So the further out, the trickier it is, but we do have a law for further out galaxies. We found that galaxies further away are moving faster and faster away from each other than those closer by. And that follows a nice mathematical law that we can use. And so Hubble's law is galaxies are receding from us at speeds proportional to their distances. And that proportional constant is 71 kilometers per second per megaparsec. Okay, that's the Hubble constant right here. So here we have V standing for the velocity. Here's the constant, the proportionality constant, the Hubble constant, which is this number 71. And then times the distance, D is the distance farther out. So if you plot velocity as a function of distance, this is what you're going to get. You're going to see some galaxies close in. And the further away you are, the faster you're moving. Okay. Galaxies further away are receding faster than those close to us. And this was published in 1929. And you have to be aware of, this is when they thought galaxies were really nebula. So those old books have been since updated. Now, mapping galaxies in modern times, this is a really significant undertaking. A lot of work done by the Sloan Digital Sky Survey, SDSS, which is in Apache Point, New Mexico. And they have been mapping these taking data since 2000 and trying to provide a map of our universe, the observable universe. So here we have each dot is a galaxy. Okay, so we haven't covered all the sky yet. So a lot of this data is being taken over by new observatories that are also adding on to what the Sloan Digital Sky Survey has done. So right now it's only still doing spectroscopy as far as doing its main collecting spectroscopy for its main data collection, but there's a lot of others that are adding on and have better cameras, and we're constantly trying to get a better visual, a map of the cosmos here. And then, just going to show you the Sloan Sky Survey. A project that's been around for a decade is Galaxy Zoo. That's a citizen science project where you could help classify galaxies by their types and by identifying the different types and different interesting features. They'll give you a bunch of galaxies based on the data that's been accumulated. And you look at these and you kind of classify them as a barred spiral, elliptical, or irregular. And you note different interesting features of these in this project, Galaxy Zoo. And that really helps a lot of the modern scientists put together these templates for understanding galaxy evolution and the overall structure of the universe. So it's really something fun to do. They actually have a smartphone app too. You can look up Galaxy Zoo on your smartphone for apps and see if you want to jump on board and help with galaxy classification. And we are just discovering so much as far as galaxies go that really, like I said, it's a lot of new science and a lot of really new updates that we're making as far as galaxies go.